about 14 billion years back, the impossible took place. Everything you see around you burst out from a spot tinier than an atom. But there's something they keep from you. That blast may not have been where it all started. New findings from Nobel Prize winners tell us our universe could be just one heartbeat in a never-ending cycle. Before our Big Bang happened, another universe might have existed, and before that one, yet another. Scientists discovered unusual warm spots in space that might be leftover signals from a universe that was here before ours. If mind-bending mysteries about the cosmos excite you, hit that subscribe button. Our exploration of what existed before everything starts right now. Think about squeezing all that exists into a space tinier than the dot at the end of this sentence. Every bit of matter, every spark of energy, all of space as we know it. Scientists call this the singularity, the spot where our universe supposedly started. But there's a huge issue that physicists don't often talk about openly. The math completely breaks down at this moment. When you work out what happened right at that instant of the Big Bang, the math gives you infinity. The temperature goes infinite. The density goes infinite. How space curves goes infinite. For someone who works with numbers, infinity isn't just a really huge number. It's a warning sign shouting that something basic has gone terribly wrong with your calculations. General relativity, Einstein's brilliant work that explains gravity and how space bends, works amazingly well almost everywhere in the universe. It tells us about black holes. It shows us why GPS satellites need their clocks adjusted. It explains how galaxies bend light. But at the singularity, general relativity stops working entirely. The idea that explains everything suddenly can't explain anything. This creates what physicists call the singularity problem. If our best explanation of gravity can't handle the most important moment in the history of the cosmos, then something crucial is missing from our understanding. Stephen Hawking spent many years struggling with this puzzle. Roger Penrose earned a Nobel Prize partly because he showed that singularities can't be avoided in Einstein's theory. Both of these brilliant minds eventually reached a bold conclusion. Maybe the singularity never really happened. Think about what that means. Every tiny piece in your body, every star shining in the sky, supposedly came from a mathematical impossibility. The whole universe appeared from a point where physics itself can't work. This isn't real science. This doesn't even come close to being an answer. The issue gets even worse when you bring quantum mechanics into the picture. Quantum physics talks about how incredibly small particles behave, and it has rules of its own that often clash with general relativity. At the unbelievably tiny scales of the singularity, quantum effects should be in charge. But we don't have a working explanation that brings quantum mechanics and gravity together. We're literally unable to see what happened at that most critical instant. Some physicists say we should just accept the singularity as when time itself began. Before that moment, there was no before. Time started ticking right at the bang. But this answer feels like giving up. It's like a detective coming across a crime scene with no tracks leading to it and saying the criminal just appeared out of thin air. Others say we need a quantum theory of gravity to see what really took place. And in the last 20 years, several such theories have come up. These new ways of thinking reveal something amazing. The singularity might not be real. Instead of starting from nothing, these theories say something was there before. Our universe might not be the opening act in cosmic history. It could be the next chapter. What if the Big Bang wasn't a beginning, but a change from one state to another? Roger Penrose isn't someone who makes crazy claims without thinking. At 94 years old, he spent 70 years working with math that most people can't even understand. He showed that the universe isn't a one-time thing. It goes through endless cycles. Each cycle starts with what we call a Big Bang and finishes in a strange, far-off future condition. Then, something amazing takes place. The end of one cycle turns into the start of the next. Our universe is just one part in a book that never ends. This isn't wild guessing from some unknown researcher. This is a Nobel Prize winner saying that everything you were taught about how the cosmos began might be incorrect. Penrose shared his full theory in a book called Cycles of Time back in 2010. The scientific community responded with both interest and doubt. Some thought it was brilliant, while others said it was impossible. What makes Penrose's thinking different from other wild theories is that it makes guesses we can actually check. He claims that violent happenings from the universe before ours should have left marks on our universe. Specifically, he searched for unusual patterns in the cosmic microwave background, the faint glow of light that fills all of space. This glow is like an old photo of the universe, showing us what things were like 380,000 years after the Big Bang. Penrose and the people working with him studied data from satellites that map this light. They claimed to discover exactly what the theory said they would find: circles of strange temperature, which they named Hawking points. These points, according to Penrose, are the final moments of huge black holes from the universe before ours. The light from those ancient black holes supposedly made it through the change and shows up as warm spots in our sky. Many scientists quickly tried to show these claims were wrong. Several research teams looked at the same information using different ways. They discovered that the circles Penrose pointed out were no more unusual than random ups and downs you'd expect by chance. The argument got intense. Papers and responses flew back and forth in science journals. Penrose didn't back down. In 2018, he shared new analysis claiming even stronger proof. He found hot spots that were much hotter than the areas around them, far beyond what random chance should create. The temperature differences were about 10 times bigger than the cosmic average. Once again, critics said that similar patterns showed up in fake universes where no previous cosmos existed. The debate goes on today. Penrose's reputation means his ideas can't be ignored, but the proof remains disputed. What's clear is this: a brilliant mind has looked at the universe and seen something others didn't notice. Whether he's right or wrong, his theory opened a door that many thought was sealed forever. The door to what was there before. To understand how one universe could turn into another, you need to grasp a strange quality of space and time. Penrose built his whole theory on something called conformal geometry. This is a type of math that looks at shapes and distances, but with a twist. It focuses on angles and paths that light takes while ignoring absolute sizes. Here's why that matters for the study of the cosmos. Picture the universe in the distant future, trillions and trillions of years from now. All stars have burned out. All matter has broken down or dropped into black holes. Those black holes themselves have disappeared through a quantum process called Hawking radiation. What's left is nearly empty space, filled only with photons, particles of light, racing away from each other as the universe grows. In this far-off future, nothing has mass anymore. Everything that could break down has broken down. The universe is cold, dark, and made up almost entirely of light spreading through expanding space. This is where Penrose saw something deep. Particles with mass feel time passing. They age. They have internal clocks. But particles without mass, like photons, don't feel time the same way. For a photon, the trip from one end of the universe to another happens right away from its own viewpoint. When the universe reaches this state of pure light with no particles that have mass, something weird becomes possible. The idea of size becomes meaningless. If you have no rulers made of atoms, no clocks made of matter, no reference points with mass, then you can't measure distances or how long things take. The universe basically loses track of its own size. Penrose realized you could take this far future universe and change it mathematically. Using conformal geometry, you can rescale it so the endless stretch of the dying universe becomes the endlessly small point of a new Big Bang. The ending and the beginning are the same event looked at from different angles. It's like looking at both sides of the same coin. This change isn't random. It keeps the geometry that matters for light and energy. The paths photons take in the old universe become the paths photons take in the new one. Information carried in light could theoretically survive the change. The new universe doesn't start from nothing. It gets structure from what came before. The rescaling solves several deep problems. In standard Big Bang theory, we have to ask why the universe started in such a special low disorder state. Entropy is how we measure disorder, and our universe began incredibly organized. Where did that organization come from? Penrose's cycles give an answer. The organization comes from the smooth, empty state at the end of the previous cycle. The far future naturally creates the low disorder conditions needed for a new start. There's another benefit. The uniformity of our universe has always confused cosmologists. Why does the cosmic microwave background look nearly the same in every direction? Why did areas of space that could never have talked to each other end up with the same temperature? Standard cosmology uses inflation, a short period of faster than light growth, to explain this. But inflation has its own fine-tuning issues. In conformal cyclic cosmology, uniformity comes naturally from the previous cycle. The long period of expansion in the old universe smooths everything out. When that smooth ending becomes the new beginning, the uniformity carries over. inflation needed. No special starting conditions required. The universe gets its properties from cosmic inheritance. Critics point out big challenges. How exactly does the change work? What happens to matter that hasn't broken down? Can information really survive such a big transformation? Penrose admits some details aren't clear, especially the physics at the crossover surface, where one cycle ends and the next starts. He says this is exactly where quantum gravity must take over, filling in the gaps that regular relativity can't handle. Whether conformal cyclic cosmology is right remains unknown. What can't be denied is its beauty. The idea that endings and beginnings are connected, that the universe is eternal and self-renewing, has a certain grace. But beauty alone doesn't make a theory true. The cosmic microwave background is the oldest light in the universe. Astronomers point their tools at empty space between galaxies. They pick up this faint glow. It comes from every direction evenly, with a temperature of about 2.7 degrees above absolute zero. This light was released 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. Scientists have mapped this glow in amazing detail. Satellites like WMAP and Planck measured tiny temperature changes across the whole sky. Some areas are slightly warmer, about 1 part in 100,000 hotter than average. Others are slightly cooler. These changes represent the seeds that eventually grew into galaxies and groups of galaxies. But Penrose wasn't looking for these well-known ups and downs. He was hunting for something totally different, circular patterns showing Hawking points. According to his theory, huge black holes from the previous universe would have slowly disappeared through Hawking radiation. This is a quantum effect where black holes slowly lose mass by giving off particles. For a black hole with billions of times the sun's mass, this process takes an impossible amount of time. We're talking about 10 to the power of 100 years, a number with 100 zeros after it. Eventually, though, each black hole would completely disappear in a final burst of energy. These bursts would be the last energetic events in the dying universe. When the conformal rescaling happened, turning the far future into a new Big Bang, these bursts would leave marks. They would show up as specific types of odd spots in the cosmic microwave background of the new universe, our universe. Penrose predicted these marks would look like circular areas where the temperature falls off in a certain way from a central hot spot. The circles would have widths about 5 times the width of the full moon in our sky. They wouldn't be obvious at first glance, but math analysis should show them. In 2010, Penrose and physicist Va Gerzadian claimed they found exactly these patterns. They scanned the WMAP satellite data and found many circles where the change in temperature was much lower than expected. They figured that the chance of seeing so many such circles by random luck was very small, less than 1 in a billion. The announcement created instant controversy. Confirmed, it would change our understanding of cosmic history completely. Several research teams rushed to check the findings. Within months, Three separate groups published disagreements. They looked at the same data and found no unusual extra circles. When they created fake universes using standard cosmology with no previous cycles, those fakes produced just as many circular patterns as the real data. The disagreement came down to method. How do you decide what counts as a real circle? How do you properly make random fakes to compare against? These technical questions became battlegrounds. Each side said the other had bad math. Not discouraged, Penrose improved his approach. In 2018, he shared new analysis with Daniel N. and Christoph Meissner. This time, instead of looking for circles with low ups and downs, they searched for bunched hot spots. They found patches in the cosmic microwave background that were much hotter than the areas around them. Around these hot spots, the temperature change was much steeper than in any of their fake universes. Not a single fake out of 1,000 matched the real data. They argued these hot spots were exactly what you'd expect from Hawking points. The final disappearance of a black hole would put huge energy into a small area. That energy would stretch during the early growth of the new universe, creating a hot patch with a certain size and temperature shape. Again, most of the community stayed doubtful. Many physicists felt the analysis was comparing different things. The fakes might not be catching all the complexity of the real universe. Other groups noted that if you search for enough different patterns in noisy data, you'll eventually find something that looks special just by chance. As of now, the existence of Hawking points remains unproven. The cosmic microwave background is one of the most carefully measured things in science. Yet, understanding its fine details is surprisingly open to interpretation. But one thing is certain. If those hot spots really are echoes from a previous universe, we're not just looking at old light. We're looking at ghosts. The universe today is messy. Galaxies bunch together in threads and sheets. Stars burn and blow up. Black holes eat matter. Disorder is everywhere. This messiness is entropy, the measure of how spread out and disorganized energy becomes over time. The second law of thermodynamics says that entropy always goes up. Everything tends toward disorder. Your room gets messy unless you actively clean it. Stars eventually burn out. Even atoms break down given enough time. Yet, the Big Bang apparently started in an incredibly organized state. This is one of the deepest puzzles in cosmology. When we look at the cosmic microwave background, we see an almost perfectly smooth universe. Temperature changes of only 1 part in 100,000. No big clumps, no major irregularities, just gentle ripples in an otherwise even sea. This amazing smoothness represents very low entropy. Where did that order come from? In the branch of physics that studies entropy, low entropy states are incredibly unlikely. Imagine throwing a deck of cards into the air. The chance that they land in perfect number order is basically 0. Now imagine that the deck has not 52 cards, but 10 to the power of 90 particles. That's roughly how many particles exist in the part of the universe we can see. The odds of them starting in such an organized setup are impossibly small. Standard Big Bang cosmology doesn't explain this starting order. It simply assumes the universe started that way. Physicists call this assumption the past hypothesis. We guess that entropy was very low at the beginning because, well, observations show it was very low. This isn't an explanation. This is just restating the puzzle with fancier words. Roger Penrose figured out just how special the starting state actually was. He estimated that the gravitational details at the Big Bang were tuned to a precision of 1 part in 10 to the power of 10 to the power of 123. Let that number sink in. It's 10 with 123 zeros after it, and then you take 10 to that power. Writing it out would need more digits than there are atoms in the universe. This is what Penrose calls the Weyl curvature hypothesis. Weyl curvature measures the type of gravitational field tied to tidal forces and gravitational waves. In an irregular, lumpy universe with black holes and collapsed structures, Weyl curvature is huge. But at the Big Bang, it was basically zero. Gravity at the beginning was incredibly smooth and even. This smoothness is the source of the universe's low starting entropy. Why would the universe start in such an absurdly unlikely state? Cosmic inflation gives one answer. If the universe went through a short period of exponential growth right after the Big Bang, that growth would have smoothed out any starting irregularities. It's like stretching a wrinkled bed sheet. Pull the edges fast enough, and the wrinkles disappear. Penrose's cyclic cosmology offers a different answer. The far future of the old universe naturally becomes smooth as space grows and matter spreads out. When that smooth ending changes into a new beginning, the low entropy carries over. The past hypothesis isn't an assumption, it's a result of cosmic recycling. But this creates another question. What about the entropy from the old universe? If entropy always increases and the new universe gets conditions from the old, shouldn't each cycle become more disordered than the last? This is called the entropy problem in cyclic cosmology. Some models suggest the universe grows slightly bigger with each cycle, giving more room for entropy. Others say black holes serve as entropy storage that somehow resets during the change. These solutions remain controversial and incomplete. The math of what happens during the bounce or change is still not fully understood. We're asking questions about physics at energy levels we can't test in labs. At the moment, we only have theories and guesses. What we do know for certain is that the universe's remarkable starting smoothness demands an explanation. Either something amazing happened before the Big Bang to set up those conditions, or the Big Bang itself was far more special than our theories say. Neither option is easy to accept. Deep beneath the smooth look of space lies something deep. Most people think of space as just emptiness, a stage where matter and energy do their cosmic dance. But quantum physics suggests reality is more complex. Even the vacuum of space has structure, and that structure might save the universe from the singularity problem. Loop quantum gravity is one of the main approaches to bringing quantum mechanics together with Einstein's general relativity. It starts with a bold idea. Space itself is not endlessly divisible. You can't keep zooming into smaller and smaller distances forever. Eventually, you hit a basic limit called the Planck length, about 10 to the power of negative 35 meters. This is 20 orders of size smaller than a proton. At this scale, space is not smooth. It's grainy, made of separate quantum units. Think of it like pixels on a screen. From far away, an image looks smooth. Up close, you see it's made of individual colored dots. Space, according to loop quantum gravity, is similarly pixelated at the Planck scale. These pixels aren't still. They're moving loops of gravitational field quantum fluctuations that weave together to form the fabric of space-time. Theory gets its name from these loops. Instead of describing gravity as the bending of smooth space, loop quantum gravity describes it as networks of connected loops. These networks are called spin networks, and they represent the quantum state of geometry itself. This picture changes everything about singularities. In regular general relativity, when matter collapses under gravity, it can compress to infinite density at a single point. Infinite density means infinite bending of space. Math blows up. Physics stops working. But in loop quantum gravity, infinite compression is impossible. You can't squeeze below the Planck scale because there's no space smaller than a Planck length. As matter collapses and density grows, quantum effects become stronger. When the density reaches the Planck density, about 10 to the power of 93 grams per cubic centimeter, something dramatic happens. Gravity itself becomes pushing instead of pulling. The collapsing matter bounces back outward. Instead of a singularity, you get a bounce. This prediction led to loop quantum cosmology, a simplified version of the full theory applied to the whole universe. In the early 2000s, physicist Martin Bojold showed that when you use loop quantum cosmology to model the Big Bang, the singularity goes away. The universe doesn't begin from an endlessly compressed point. It rebounds from a previous shrinking phase. Imagine running cosmic history backwards. Galaxies get closer together. The universe gets smaller and denser. In standard cosmology, you eventually hit the singularity and your math breaks. In loop quantum cosmology, as you approach the Planck density, quantum pushing takes over. The shrinking reverses into growth. There's no moment of infinite density. The Big Bang becomes a big bounce. Detailed computer models confirm this behavior. Researchers moved quantum states of the universe forward and backward through the bounce point. Quantum affects smoothly connected shrinking and growing phases. Crucially, some information from the shrinking phase survived the bounce. The volume of the universe at its smallest point and the rate of growth after the bounce depended on conditions before the bounce. This means we could potentially learn about the pre-bounce universe by studying our current universe. Observations of the cosmic microwave background, or how galaxies are spread out, might contain signs of quantum gravity effects during the bounce. These would be amazingly subtle signals, but they'd be real. Loop quantum cosmology also solves another puzzle, the horizon problem. In standard cosmology, distant areas of the universe that have never talked to each other somehow have nearly identical properties. How did they match their temperatures? Inflation gives one answer by making the observable universe come from a tiny connected area that then grew rapidly. Loop quantum cosmology offers another way. During the shrinking phase before the bounce, areas that are now far apart were once in contact. They came to balance back then. When the universe bounced and grew, that balance was kept. No inflation needed. The theory isn't without challenges. Loop quantum gravity itself is incomplete. We don't yet have a full math setup that works in all situations. The cosmological models are simplified, assuming perfect balance that the real universe doesn't have. Extending the theory to less balanced situations is incredibly hard. Moreover, some physicists question whether loop quantum gravity is the right approach at all. Competing theories like string theory take completely different paths to quantum gravity. Each approach makes different predictions about what happens at the Planck scale. What's clear is that quantum effects at the smallest scales can have cosmic results at the largest scales. Space itself might be the key to understanding where we came from. For decades, the Big Bang was cosmology's founding story. Everything started from a single point 13.8 billion years ago. Before that moment, nothing existed. Not space, not time, not even the laws of physics. The Bang was the absolute beginning, and asking what came before was considered meaningless or even unscientific. That certainty is falling apart. Multiple separate lines of research now point toward a bounce rather than a bang. Not a creation from nothing, but a change from something earlier. The universe didn't begin. It changed form. This shift in viewpoint is as deep as the Copernican revolution that removed Earth from the center of the cosmos. The Big Bounce hypothesis comes in several versions, but they share core elements. Our universe was preceded by a shrinking phase. As that previous universe collapsed, instead of forming a singularity, quantum gravity effects stepped in. Pushing quantum forces stopped the collapse and reversed it into growth. This reversal is the bounce. Loop quantum cosmology provides the most developed framework for understanding the bounce. As discussed earlier, the separate structure of space at the Planck scale prevents infinite compression. When matter density reaches critical values, roughly 10 to the power of 93 grams per cubic centimeter, quantum corrections to Einstein's equations become dominant. These corrections include a pushing term that grows rapidly at extreme densities. The math shows that the bounce isn't instant. There's a brief quantum time lasting about 10 to the power of negative 43 seconds, where regular notions of space and time break down. During this period, the universe passes through its minimum volume. Then, quantum pushing takes over completely and drives the growth we observe. What happened in the shrinking universe before the bounce? Here, the evidence becomes guesswork. Some models suggest the previous universe was similar to ours, with galaxies and stars just running in reverse time. Others propose the shrinking phase had very different properties. The matter content, the spatial shape, even the effective constants of nature might have been different. One interesting possibility is that information could survive the bounce. Unlike black hole singularities, where information appears to be destroyed, the bounce is smooth enough that quantum states might pass through. The fields representing matter and energy evolve continuously. Their values after the bounce depend on their values before. This creates what physicists call a quantum bridge, connecting the two phases. If information survives, then leftover traces from the pre-bounce universe could exist in ours. These wouldn't be physical objects. Atoms and molecules couldn't survive the extreme conditions near the bounce. But subtle connections in the quantum fields might last. These connections could show up as specific patterns in cosmic observations. Several research groups have calculated what the cosmic microwave background should look like if our universe bounced. The predictions depend strongly on the details of the bounce dynamics, but some general features appear. The range of temperature ups and downs might have slight differences from the standard predictions. The amount of gravitational waves made during the bounce could differ from inflation. How matter is spread on large scales might carry subtle signs. So far, observations haven't clearly detected any bounce signatures. The cosmic microwave background matches standard inflationary predictions remarkably well, but the accuracy of current measurements is limited. Future experiments with higher sensitivity might reveal small oddities that point to a bounce. Critics raise several disagreements to bounce cosmology. The biggest concern is whether the bounce truly avoids a singularity or merely delays it. Some analyses suggest that even with quantum corrections, certain types of uneven collapses still lead to singularities. If the universe wasn't perfectly balanced before the bounce, would it still bounce cleanly? Another worry is fine-tuning. For a bounce to produce a universe like ours, conditions at the bounce point must be carefully arranged. The quantum state needs specific properties. The amount of matter and how it's spread must fall within narrow ranges. If the pre-bounce universe was chaotic and irregular, could the bounce really smooth everything out? These technical debates continue in science journals. What's remarkable is that mainstream physics now seriously considers the possibility of a pre-existing universe. The Big Bounce is no longer fringe guessing. It's a legitimate scientific guess with mathematical strength and potential observational tests. The implications are staggering. If the bounce is real, then the universe has a history extending endlessly into the past. Or perhaps there was an earliest bounce, a first change, and the mystery simply moves back to that moment. Either way, the Big Bang loses its status as the ultimate start. We're not witnessing the beginning of existence. We're watching one phase in an ongoing process. The idea of universes connected by a quantum bridge sounds like science fiction. But in loop quantum cosmology, it comes naturally from the math. This bridge isn't a physical structure you could see or touch. It's a continuous mathematical evolution that links the shrinking phase to the growing phase without ever reaching zero volume. To understand the quantum bridge, you need to grasp how quantum mechanics treats evolution. In classical physics, objects have definite positions and speeds at each moment. You can predict exactly where a ball will be if you know where it started and how fast it was moving. In quantum mechanics, particles don't have definite positions until measured. They exist in overlapping positions spread across multiple possible locations at the same time. The universe in loop quantum cosmology is described by a quantum state, a mathematical object called a wave function. This wave function holds the probabilities of finding the universe with different volumes and matter contents. As time moves forward, the wave function evolves according to quantum equations. This evolution is unitary, meaning information is kept and nothing is truly lost. When the universe shrinks, its wave function evolves towards smaller and smaller volumes. In classical general relativity, this evolution would hit a singularity at zero volume and stop. The equations would produce infinities and meaningless results. But in loop quantum cosmology, the evolution doesn't stop. The wave function smoothly passes through the region of minimum volume and comes out on the other side, corresponding to a growing universe. This passage through the minimum is the quantum bridge. It's called a bridge because it connects two distinct cosmic phases. Before the bridge, the universe was shrinking. After the bridge, the universe grows. The bridge itself lasts for the briefest instant, roughly 1 Planck time, about 10 to the power of negative 43 seconds. During this instant, classical concepts like volume and time become fuzzy. You can't ask what was the exact volume at this precise moment. The question assumes a level of certainty that quantum mechanics doesn't allow at such extreme scales. What you can ask is what's the probability distribution for volumes, and how does that distribution evolve? Calculations show the distribution stays well behaved throughout the bounce. It doesn't spike to infinity. It doesn't develop breaks. The universe doesn't blink out of existence and reappear. It continuously exists as a quantum system, even if our classical instincts about space and time fail. One key feature of the quantum bridge is that it preserves certain quantities called observables. In quantum mechanics, observables are properties you can in principle measure. For cosmology, important observables include the total energy content, the spatial curvature, and the values of various matter fields. The quantum bridge allows these observables to pass through the bounce point with specific relationships kept. For example, consider a scalar field representing a type of matter. This field has a value at each point in space and evolves over time. If you know the field's behavior during shrinking, you can calculate its behavior after the bounce using loop quantum cosmology. The two are linked. The scalar field after doesn't start with random values. It gets structure from the scalar field before. This inheritance is crucial for making predictions. If we can measure the properties of our universe carefully enough, we might be able to rebuild properties of the pre-bounce universe. This would be indirect detection, like figuring out the shape of an object from its shadow. The measurements would be amazingly difficult, requiring precision beyond current technology. But they're possible in principle. Different scalar fields might carry different types of information. Inflattened fields, if they exist, could hold data about pre-bounce energy densities. Curvatin fields might preserve information about spatial geometry. Even the pattern of quantum fluctuations seeded during the bounce could reflect pre-bounce conditions. However, not all information survives. There's an effective uncertainty principle operating at the bounce. Just as you can't know both a particle's position and momentum with perfect precision at the same time, you can't know all properties of the pre-bounce and post-bounce universes with perfect precision at the same time. Some details are inevitably lost or scrambled by the quantum nature of the bounce. Physicists describe this using a transfer function, a mathematical rule that maps pre-bounce states to post-bounce states. The transfer function is not one-to-one. Multiple different pre-bounce states could lead to the same post-bounce state. This means we can't uniquely determine the entire history of the shrinking universe just by studying the growing one. Some uncertainty is fundamental. Despite this limitation, the quantum bridge represents a deep shift in cosmological thinking. It suggests the universe is not broken into disconnected time periods. Past, present, and future are linked by continuous quantum evolution. The bounce is not a wall blocking our knowledge. It's a gateway, admittedly narrow and unclear, but a gateway nonetheless. What lies on the other side of the quantum bridge remains largely mysterious, but we now have theoretical tools to probe it. The bounce is no longer an impenetrable barrier. It's a window, however cloudy, into a realm we once thought was forever hidden. In 1980, physicist Alan Guth proposed something revolutionary. The universe, he said, went through a period of incredibly rapid expansion in its first moments. In less than a trillionth of a trillionth of a trillionth of a second, the universe doubled in size at least 90 times. Space grew faster than light. This rapid growth smoothed out irregularities and flattened the geometry, solving several major cosmic puzzles. Inflation quickly became the leading theory of the early universe, but as physicists explored the math more deeply, they discovered something unexpected. Inflation doesn't just happen once and stop everywhere at the same time. In most versions of the theory, inflation is eternal. Once it starts, it never completely ends. Here's how eternal inflation works. Imagine the universe filled with an energy field called the inflaton. This field drives inflation when its energy density is high. As inflation goes on, the field gradually decays into lower energy states. In regions where it decays, inflation stops and a hot Big Bang begins. That region becomes a pocket universe like ours. But here's the catch. Space is growing exponentially. Even though inflation ends in some places, the growing regions between those places expand faster than the non-inflating regions can fill them. New volume is created faster than old volume can convert. The total amount of inflating space increases without limit. More and more pocket universes form forever. Think of it like foam on the ocean. Each bubble represents a pocket universe where inflation ended. The foam between bubbles is still inflating, creating new bubbles endlessly. You can pop individual bubbles, but the foam itself never stops growing. The process is self-sustaining and eternal into the future. Quantum fluctuations make this inevitable. The inflattened field is subject to quantum jitter. In some tiny patches, random fluctuations push the field up the energy hill instead of down. Those patches inflate longer and produce more volume. Even if inflation is unlikely to start, once it starts anywhere, it runs away exponentially. The inflating regions dominate the universe's total volume. Andre Linde, one of the pioneers of inflation theory, proved in 1986 that eternal inflation is generic. You don't need special conditions. Almost any inflation model leads to eternal inflation unless you carefully design the theory to avoid it. Guth confirmed this in later work. He famously said, "It's hard to build models of inflation that don't lead to a multiverse. The multiverse arising from eternal inflation is vast beyond comprehension. It's not just billions of pocket universes. It's infinite. Every possible way that inflation could end happens infinitely many times in different places. Every possible set of physical constants that could emerge from the inflatten's decay appears somewhere. This leads to amazing conclusions. In an infinite multiverse, everything that can happen does happen. Not just once, but infinitely many times. There are infinite copies of Earth, infinite copies of you, infinite versions where you made different choices, infinite universes with different physics entirely. Most physicists find this deeply unsettling. Science is supposed to make predictions, but if anything possible occurs somewhere in the multiverse, how do you predict what we should observe in our universe? This is called the measure problem. You can't calculate probabilities in the usual way when dealing with infinity. Some physicists embrace the multiverse as a feature, not a bug. It explains the cosmological constant problem. In our universe, the vacuum energy density is incredibly small, about 10 to the power of negative 120 in natural units. Theory suggests it should be 10 to the power of 120 times larger. Such a massive difference seems impossible to explain. But in a multiverse with infinite variety, some universes will randomly have small vacuum energy. We live in one of those because universes with large vacuum energy don't form stable galaxies and stars. Observer selection does the rest. Other physicists hate this reasoning. They argue it's giving up on fundamental physics. Instead of deriving the cosmological constant from first principles, the multiverse says it's just environmental, like asking why Earth's distance from its star is 93 million miles. The answer isn't deep physics. It's just that we need the right distance for liquid water and life. This divide runs deep in modern cosmology. Is the multiverse a real consequence of our best theories, or a sign we've gone wrong somewhere? The debate rages on. What's undeniable is that inflation, the theory meant to explain the early universe, has led us to question whether our universe is all that exists. Loop quantum cosmology focuses on quantum gravity effects, but there are other bounce scenarios. One alternative involves matter itself having exotic properties that create bouncing behavior. These are called matter bounce models. In standard cosmology, matter becomes denser as the universe shrinks. Eventually, density reaches infinity at the singularity. But what if matter doesn't behave normally at extreme densities? What if there are fields or particles with unusual equations of state that become dominant when things get compressed? Some theoretical particles have negative pressure. Pressure is usually positive. Particles push outward. But in certain quantum field theories, effective pressure can be negative, which means the field pulls inward. More importantly, extremely negative pressure can violate the energy conditions that lead to singularities in general relativity. Energy conditions are assumptions about how matter and energy behave. Einstein's equations allow almost any kind of matter in principle, but physicists impose energy conditions to rule out unphysical situations. The most important is the null energy condition, which says that energy density plus pressure must be non-negative. If matter violates this condition, singularities can be avoided. The contracting universe approaches a minimum size, but before reaching zero volume, the exotic matter creates enough repulsion to reverse the collapse. The universe bounces without needing modifications to gravity itself. Ghost condensate models are one example. These involve scalar fields with unusual kinetic terms. Under normal conditions, they behave like ordinary matter, but at high densities, they condense into a state with strongly negative pressure. This pressure becomes repulsive and drives the bounce. Ekpyrotic models take a different approach. Originally developed in the context of string theory and extra dimensions, ekpyrotic scenarios propose that our universe is a three-dimensional surface, a brain in a higher dimensional space. Another brain exists parallel to ours. Periodically, these brains collide. Each collision corresponds to a big bang in our universe. In the ekpyrotic picture, the universe undergoes cycles of slow contraction, collision, and expansion. During the slow contraction phase, irregularities are smoothed out by a different mechanism than inflation. The collision itself is violent, but not infinitely so. Higher dimensional physics regulates the process, preventing a singularity. These brain collisions can repeat indefinitely, creating a cyclic universe without beginning or end. Each cycle might last trillions of years. Our Big Bang was just the most recent collision in an eternal sequence. Matter bounce models have some advantages over loop quantum cosmology. They don't require modifying the fundamental structure of space. They work within general relativity, just with unusual types of matter. This makes them easier to analyze with existing mathematical tools. However, they face their own challenges. The exotic matter needed for the bounce often has disturbing properties. Fields with strongly negative pressure can have negative energy density, which leads to instabilities. Quantum mechanically, such fields might decay or produce infinite numbers of particles. Making the matter bounce work consistently with quantum theory is difficult. Moreover, most exotic matter scenarios require fine-tuning. The fields must have very specific properties to produce a bounce at just the right moment. If the parameters are slightly off, you either get a singularity or a universe that bounces too early or too late, producing the wrong cosmic conditions. Despite these issues, matter bounce cosmology remains an active research area. Some physicists prefer it to quantum gravity approaches because it's more conservative. Rather than rethinking the nature of space itself, it explores possibilities within established frameworks. Whether the bounce comes from quantum gravity or exotic matter, the conclusion is similar. The Big Bang wasn't the beginning. It was a transition. Something came before, and that something left traces we might one day detect. Dark energy is one of the strangest discoveries in cosmology. In the late 1990s, astronomers measuring distant supernovae found that the universe's expansion is accelerating. Galaxies aren't just moving apart, they're moving apart faster and faster. This acceleration requires a form of energy that fills all of space and pushes outward. We call it dark energy, but we don't know what it is. The simplest explanation is a cosmological constant, a form of energy built into the vacuum of space itself. Einstein's equations allow such a term. In fact, Einstein originally added it to his equations for different reasons, then removed it, calling it his greatest blunder. Dark energy makes up about 68% of the universe's total energy. Matter, both ordinary and dark, accounts for only 32%. The universe is dominated by something we don't understand. Dark energy plays a crucial role in cyclic models of the universe. In Penrose's conformal cyclic cosmology, dark energy is what drives the far future universe toward the smooth, empty state that becomes the next Big Bang. As matter decays and black holes evaporate, dark energy remains. Its constant density means that as space expands, more dark energy appears. Eventually, dark energy completely dominates. The universe in this far future state is called de Sitter space, named after Willem de Sitter, who studied such solutions to Einstein's equations. De Sitter space is empty except for the cosmological constant. It expands exponentially, doubling in size at regular intervals. This expansion never ends. It goes on forever. In standard cosmology, this is the ultimate fate of our universe. We're headed toward cold, dark, eternal expansion. Nothing particularly interesting happens after the last stars burn out and the last black holes evaporate. The universe just keeps expanding into emptiness. But Penrose saw something different. He noticed that de Sitter space has unusual properties when you think about it from the perspective of light. Photons traveling through de Sitter space lose energy due to the expansion. They become redshifted. In the infinite future, their wavelength becomes infinite. Their energy becomes zero. This limiting state, infinitely redshifted radiation in an expanding universe, can be conformally rescaled. Using the same mathematical tricks Penrose applied to the far future, you can transform de Sitter space into a new Big Bang. The infinite future becomes an infinite past for a new cycle. This idea sounds crazy, but the math works. The conformal structure of space-time allows such transformations. Time itself becomes flexible when you're dealing with geometries where nothing has mass and nothing provides a natural clock. Other cyclic models use dark energy differently. In some ekpyrotic scenarios, dark energy doesn't stay constant. It's a dynamical field that changes over time. During one phase of the cycle, it acts like normal dark energy, accelerating expansion. During another phase, it changes character and drives contraction. The cycling happens because the field rolls up and down its potential energy curve repeatedly. These models require dark energy to have properties beyond a simple cosmological constant. They need it to be a field that can evolve, called quintessence. Some theoretical models of quintessence do allow such behavior, but they're speculative. We have no direct evidence that dark energy is anything other than a constant. Dark energy also creates problems for cyclic models. If each cycle undergoes accelerated expansion driven by dark energy, how do you transition from expansion to contraction? In a universe with a cosmological constant, expansion never stops. You need some mechanism to overcome the dark energy and reverse the expansion. One proposal involves quantum tunneling. The universe might quantum mechanically tunnel from an expanding state to a contracting state. In quantum mechanics, systems can jump between states even when classically forbidden. Perhaps the universe as a whole can do the same. Another idea is that dark energy isn't truly constant, even if it appears so now. Over extremely long timescales, far longer than the current age of the universe, it might decay or change. If dark energy eventually weakens, gravity could take over and pull the universe back into contraction. These remain speculative ideas. What's clear is that dark energy is deeply connected to the universe's ultimate fate, and in cyclic models, to its ultimate past as well. Understanding dark energy is crucial to understanding whether the cosmos truly cycles. Black holes are regions where gravity is so strong that nothing, not even light, can escape. General relativity predicts their existence, and astronomers have detected many of them. They range from stellar mass black holes formed by collapsing stars to supermassive black holes millions or billions of times heavier than the Sun, sitting at the centers of galaxies. In classical general relativity, black holes are perfect information destroyers. Anything that falls past the event horizon, the point of no return, is lost forever. The outside universe can never see it again. The object falls inexorably toward the central singularity and is crushed out of existence. But in the 1970s, Stephen Hawking discovered that black holes aren't completely black. Quantum effects near the event horizon cause black holes to emit radiation, now called Hawking radiation. This radiation carries energy away from the black hole. Over immense timescales, the black hole slowly shrinks and eventually evaporates completely. This creates a paradox. If a black hole evaporates, what happens to the information about everything that fell in? In quantum mechanics, information can't be destroyed. The universe's total information content is conserved. Every process is reversible in principle. But if a black hole evaporates completely, the information seems to disappear. This is the black hole information paradox. Physicists have debated this paradox for 50 years. Some argue that information is destroyed and quantum mechanics must be modified. Others say information somehow escapes in the Hawking radiation, encoded in subtle correlations. Recent work suggests that the information might be preserved in complex quantum entanglement between the radiation and the remaining black hole. This debate connects to cosmology through cyclic models. If the universe bounces or cycles, does information survive the bounce? Is the bounce more like black hole evaporation, where information is scrambled and hidden? Or is it more like ordinary evolution, where information passes through clearly? In Penrose's conformal cyclic cosmology, information does pass through. The Hawking points, the remnants of black holes from the previous universe, carry information forward. These supermassive black holes are the last structures to evaporate in the dying universe. Their final bursts of radiation supposedly leave imprints that survive the conformal transition. If Penrose is right, then black holes are not just features of our universe. They're the carriers of information between universes. They're cosmic memory banks, storing data about the previous cycle and passing it to the next. This is a beautiful idea, but it's controversial. Many physicists doubt that information can survive such a drastic transition. The conformal rescaling is so extreme, transforming infinite time into zero time, infinite size into zero size, that it seems impossible for any meaningful structure to persist. Loop quantum cosmology offers a different perspective. In the quantum bounce, information passes through the bounce point as part of the quantum state. The wave function evolves continuously. There's no moment where information is destroyed. The bounce is unitary, meaning it preserves information just like all quantum processes. However, information preservation doesn't mean you can reconstruct everything about the previous universe. The transfer through the bounce might be noisy, adding uncertainty. Some fine details might be lost, while gross features survive. It's like making a photocopy of a photocopy. The general content remains, but some sharpness is lost. If information from previous cycles exists in our universe, could we detect it? This is where cosmology becomes almost archaeological. We'd be searching for fossils, traces of ancient structures preserved in the cosmic background. The cosmic microwave background is the most obvious place to look. Any information passing through the bounce or conformal transition should affect the initial conditions of our universe. Those initial conditions are frozen into the microwave background. Statistical analysis might reveal non-random patterns that point to a previous cycle. Gravitational waves offer another potential window. The bounce or transition might generate specific gravitational wave signals. These waves would have incredibly long wavelengths today, but future detectors might be sensitive enough to spot them. The search for such signals is just beginning. For now, they remain theoretical possibilities, but the fact that we can even contemplate detecting information from before the Big Bang represents a profound shift in cosmology. The horizon problem is one of the most puzzling features of our universe. When we look at the cosmic microwave background, we see that regions on opposite sides of the sky have nearly identical temperatures. They match to within 1 part in 100,000. This is strange because these regions are so far apart that light hasn't had time to travel between them since the Big Bang. If they've never communicated, never exchanged information, how did they end up at the same temperature? In normal physics, when you have two objects that come to the same temperature, it's because they've been in contact. Heat flows from the hotter object to the cooler one until they equalize. But regions separated by billions of light years couldn't have equalized this way. They're causally disconnected, outside each other's observable range. Inflation solves this problem elegantly. If the universe underwent a brief period of exponential expansion very early on, then regions now far apart were once close together. They were in contact before inflation came to equilibrium, then were stretched apart by the rapid expansion. The uniformity we see today reflects the uniformity established when everything was compact. This is inflation's greatest success. It explains why the universe looks the same in all directions without requiring special initial conditions. The uniformity emerges naturally from the inflation process. But bounce cosmologies offer an alternative solution. If the universe existed before the bounce, then distant regions could have been in contact during the previous cycle. Consider a contracting universe. As it shrinks, regions that are far apart come closer together. Eventually, they can communicate and equalize their properties. When the bounce happens and the universe begins expanding again, this equilibrium is preserved. The regions that came into contact during contraction are carried apart by the expansion. What we observe as causally disconnected regions with matching temperatures are actually regions that were in contact before the bounce. In this picture, the horizon problem isn't really a problem. It's a natural consequence of a cyclic universe. No inflation needed. The shrinking phase of the previous cycle does the work that inflation does in standard cosmology. Loop quantum cosmology models this explicitly. Simulations show that irregularities in the contracting phase get smoothed out as the universe approaches the bounce. The quantum effects that create the bounce also act as a homogenizing force. The universe emerges from the bounce more uniform than it went in. This is important because one criticism of bounce models is whether they can produce the observed uniformity. Skeptics ask, if the universe was chaotic before the bounce, how does the bounce create order? The answer, according to loop quantum cosmology, is that the extreme conditions near the bounce naturally smooth things out. Quantum repulsion operates uniformly, pushing all regions outward at similar rates. Ekpyrotic models propose yet another mechanism. During the slow contraction phase, sound waves can travel across the universe. These sound waves smooth out density variations. As the universe slowly contracts over trillions of years, sound has time to propagate everywhere, equalizing conditions. When the collision and bounce occur, this smoothness is converted into the uniformity we we observe. Each of these explanations, inflation, quantum bounce, ekpyrotic contraction, solves the horizon problem, but in different ways. They make subtly different predictions. The pattern of temperature fluctuations, the spectrum of density variations, the amount of gravitational waves, these details differ depending on which mechanism operated. Current observations don't yet distinguish definitively between these scenarios. The cosmic microwave background matches inflation predictions well, but bounce models can be tuned to match equally well. Future measurements with higher precision might break the degeneracy and tell us which mechanism actually shaped our universe. Gravitational waves are ripples in space-time itself, traveling at the speed of light. Einstein predicted them in 1916, but they weren't directly detected until 2015, when LIGO observed waves from colliding black holes. Since then, gravitational wave astronomy has opened a new window on the universe. Cosmological gravitational waves are different from the waves LIGO detects. LIGO observes high-frequency waves from violent events like black hole mergers. Cosmological waves have much longer wavelengths, stretched by the expansion of space. They were created in the very early universe and have been propagating ever since. These primordial gravitational waves carry information about the earliest moments of cosmic history. Inflation predicts a specific spectrum of gravitational waves created by quantum fluctuations during the rapid expansion. Detecting these waves would confirm inflation and tell us about the energy scale at which it occurred. Bounce cosmologies also predict gravitational waves, but with different characteristics. The bounce itself, the moment of maximum compression and reversal, should generate gravitational waves. The spectrum depends on the details of the bounce dynamics. Is it smooth or chaotic? How long does it last? What quantum state describes the universe at the bounce point? Loop quantum cosmology predicts a characteristic spectrum. Waves generated during the bounce have specific frequency peaks corresponding to the physical processes operating at the Planck scale. These peaks would be incredibly faint and at very low frequencies, but they'd be distinguishable from inflation predictions. Ekpyrotic models make different predictions still. The slow contraction phase produces gravitational waves through a different mechanism than inflation. The resulting spectrum has less power at low frequencies. This could be tested by future space-based gravitational wave detectors. The challenge is that primordial gravitational waves are extraordinarily difficult to detect. They interact very weakly with matter. Even when they pass through us, we don't feel them. Detecting them requires incredibly sensitive instruments looking for minuscule effects. One method uses the cosmic microwave background. Gravitational waves affect the polarization of the background radiation, the direction in which light waves oscillate. Specifically, they create a pattern called B-mode polarization. Several experiments are currently searching for this signal. In 2014, the BICEP-2 experiment announced detection of B-mode polarization, which would have been the first evidence of primordial gravitational waves. The scientific community erupted in excitement. If confirmed, it would be one of the greatest discoveries in cosmology. However, subsequent analysis showed the signal was likely caused by dust in our galaxy rather than primordial waves. The search continues. Future experiments with higher sensitivity and better control of foregrounds might succeed. Space-based detectors like LISA will search for gravitational waves at different frequencies, probing different aspects of cosmic history. The Big Bang Observer, a proposed future mission, would specifically target the frequency range where bounce models predict distinctive signals. If we detect primordial gravitational waves and measure their spectrum precisely, we'll have a powerful tool for distinguishing between cosmological models. The spectrum is like a fingerprint. Each process leaves unique marks. Inflation, quantum bounce, ekpyrotic contraction, each produces recognizable patterns. This is how science advances. Competing theories make different predictions. Observations test those predictions. Gradually, we narrow down the possibilities and converge on the truth. We're not there yet for the origin of the universe, but gravitational waves offer a path forward. The measure problem is one of the most vexing issues in cosmology. It arises whenever you try to calculate probabilities in an infinite universe. If space is infinite and contains infinitely many regions, how do you define what's typical or likely? This problem becomes acute in eternal inflation. As discussed earlier, inflation creates infinitely many pocket universes with different properties. In principle, everything possible happens infinitely many times. So how do you predict what we should observe? You might say, just calculate the fraction of universes with property x, but infinity divided by infinity isn't well defined. There are infinitely many universes where the cosmological constant is small and infinitely many where it's large. Which infinity is bigger? The question doesn't make sense without additional structure. Physicists have proposed various measures, mathematical schemes for assigning probabilities in infinite spaces. Each measure gives different answers. Some predict we should be typical observers in typical universes. Others predict we should be in unusual universes. The choice of measure dramatically affects conclusions. Yet, there's no consensus on which measure is correct. This problem also appears in cyclic cosmologies. If the universe has undergone infinitely many cycles stretching into the past, which cycle should we consider ourselves in? Are we in a typical cycle or an unusual one? Penrose's conformal cyclic cosmology approaches this differently. In his model, the cycles aren't all identical. Each cycle grows in size. The crossover from one cycle to the next involves a conformal rescaling, but the physics of each cycle is similar. This creates a direction of time. Cycles get progressively larger. In this picture, we're in some particular cycle, perhaps the millionth or trillionth, but definitely not an arbitrary one from an infinite set. The measure problem is reduced, though not eliminated entirely. You still have to explain why we're in this cycle rather than an earlier or later one. Loop quantum cosmology typically focuses on a single bounce, not an infinite sequence. The universe existed before the bounce, but whether there were previous bounces is an open question. Some versions predict only one bounce, a unique moment when the universe transitioned from contraction to expansion. Others allow multiple bounces, extending indefinitely into the past. If there's only one bounce, the measure problem doesn't arise. We're in the universe that bounced. End of story. If there are infinitely many bounces, the problem returns. Do conditions change from bounce to bounce? Does the universe grow or shrink with each cycle? Does it eventually settle into a stable pattern? These questions touch on deep issues in probability and cosmology. Some physicists argue the measure problem indicates we're on the wrong track. If our best theories lead to uncomputable probabilities, maybe they're not truly our best theories. Perhaps we need a radically different framework. Others argue the measure problem is a technical issue that will eventually be solved. Just as physicists figured out how to handle infinities in quantum field theory through renormalization, we'll figure out how to handle infinities in cosmology. A third view is that the measure problem exposes a fundamental limitation. Maybe the universe is truly infinite and diverse in ways we can't fully comprehend. Our theories might be correct, but incomplete. We can describe local physics perfectly while lacking a global description that encompasses everything. This relates to a philosophical question. Is cosmology truly a science? Science traditionally makes predictions that can be tested. But if we can only observe one universe, one cycle, one bounce, how do we test theories about the multiverse or infinite cycles? We can't observe other universes or previous cycles directly. Cosmologists respond that we can test these theories indirectly. They make predictions about what we should observe in our universe. The cosmic microwave background, gravitational waves, the distribution of galaxies, these observables constrain the theories. If Penrose's Hawking points exist, they're evidence for previous cycles. If gravitational waves have a particular spectrum, they're evidence for a bounce or inflation. Science is always indirect in this way. We can't observe electrons directly, but we can observe their effects. We can't visit the center of the sun, but we can infer its temperature from neutrinos. Cosmology is more extreme, requiring inference across billions of years and potentially across cosmic transitions. But the logic is the same. The measure problem remains unresolved. It's an active area of research where progress is slow and frustrations are high. But it's also a sign of how far cosmology has come. A century ago, we didn't even know other galaxies existed. Now we're wrestling with how to define probability across infinite universes. So what can we actually test? What observations would tell us whether the universe bounced, cycled, or inflated? Several types of measurements are crucial. First, the cosmic microwave background. This is our richest source of information about the early universe. Temperature maps from Planck and other satellites show us the conditions 380,000 years after the Big Bang with exquisite detail. But we're still extracting information. Polarization measurements are particularly important. They tell us about gravitational waves and other directional effects that temperature alone doesn't reveal. Future experiments like CMB-S4, a network of ground-based telescopes, will measure polarization more precisely than ever before. Specific signatures to look for include non-Gaussianity, deviations from a perfectly smooth random distribution. Inflation predicts extremely Gaussian initial conditions. Bounce models and ekpyrotic scenarios often predict small non-Gaussian features. These would appear as correlations between temperature fluctuations at different scales. Another test involves measuring the spectral index, how the amplitude of fluctuations varies with scale. Different early universe scenarios predict different spectral indices. Inflation predicts an index slightly less than 1, which matches observations well, but future measurements with smaller error bars might reveal deviations that favor bounce models. Hawking points, if they exist, would be definitive evidence for Penrose's cyclic cosmology. The challenge is distinguishing real Hawking points from random fluctuations. This requires sophisticated statistical analysis and may require data from future satellites with better angular resolution. Second, gravitational wave observations. As discussed, different scenarios predict different gravitational wave spectra. Current gravitational wave detectors like LIGO operate at frequencies too high to see primordial signals, but planned detectors will cover lower frequencies. LISA, scheduled to launch in the 2030s, will detect waves with periods from seconds to hours. The Big Bang Observer, still in the concept phase, would detect even lower frequencies corresponding to cosmological scales. These instruments could distinguish between inflation and bounce models based on spectral shape. Third, large-scale structure. The distribution of galaxies and dark matter across cosmic scales encodes information about initial conditions. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies. Future surveys like Euclid and the Vera Rubin Observatory will map billions. By analyzing the clustering patterns, astronomers can constrain early universe physics. Different inflationary models produce different amounts of clustering at different scales. Bounce models can be similarly constrained. The key is measuring precisely enough to distinguish subtle differences. Fourth, precision cosmology parameters. The Hubble constant, the matter density, the dark energy density, these fundamental numbers tell us about the universe's composition and evolution. Tensions between different measurements, like the current Hubble tension, might indicate new physics. If the universe bounced, there might be subtle effects on these parameters that differ from standard Big Bang predictions. For example, the amount of dark matter or the primordial helium abundance might be slightly different if nucleosynthesis occurred in a post-bounce environment versus a singular Big Bang. Fifth, philosophical and theoretical consistency. Even without direct observations, theories must be internally consistent. They must connect smoothly to established physics in tested regimes. They must avoid infinities and paradoxes. They must make contact with quantum mechanics and thermodynamics. These criteria have already ruled out many proposed cosmologies. Theories that predict too much disorder, violate energy conservation, or require impossibly fine-tuned initial conditions are discarded even before observational tests. The interplay between theory and observation is what makes cosmology scientific despite its unique challenges. Theories are developed based on fundamental physics. They make predictions. Observations test those predictions. Theories are refined or discarded. The cycle continues, gradually narrowing possibilities. We're living in a golden age of cosmology. Data from multiple sources is pouring in. Theoretical tools are becoming more sophisticated. Computation power allows detailed simulations. Questions that seemed purely philosophical a generation ago are now empirically testable. Whether the universe bounced, cycled eternally, inflated, or began in a true singularity, we may know the answer within our lifetimes. The observational programs are underway. The theoretical frameworks are in place. What we need now is patience, precision, and perhaps a bit of luck. The quest to understand the universe's origin is humanity's most ambitious scientific endeavor. It asks not just how things are, but why they are at all. It probes the boundary between physics and metaphysics, between science and philosophy. For most of human history, these questions belonged to religion and myth. Every culture had creation stories, cosmic eggs, primordial waters, acts of divine will. These stories provided meaning and structure, even if they couldn't be tested. Science changed that. Starting with Galileo and Newton, we learned that nature follows mathematical laws. Those laws can be discovered through observation and experiment. The universe becomes comprehensible. The Big Bang Theory, developed in the 20th century, brought scientific rigor to cosmology. For the first time, we had a physical explanation for the universe's origin supported by evidence. But as we've seen, the Big Bang Theory has problems. The singularity is a place where physics breaks down. The initial conditions seem impossibly special. This has driven physicists to look beyond the Big Bang. What came before? Is there a before? These questions no longer seem meaningless or unscientific. They have potential answers in quantum gravity, cyclic cosmologies, and multiverse theories. Roger Penrose's conformal cyclic cosmology suggests the universe is eternal, passing through infinite cycles. Each cycle begins with a conformally rescaled Big Bang and ends with a far future that becomes the next beginning. Information from previous cycles might survive as Hawking points in the cosmic microwave background. Loop quantum gravity suggests space is fundamentally discrete at the Planck scale. This discreteness prevents singularities. The Big Bang becomes a big bounce, a transition from a previous contracting phase to our current expanding phase. Quantum effects near the bounce create a bridge connecting the two phases. Ekpyrotic scenarios invoke extra dimensions. Our universe is a brain colliding periodically with another brain. Each collision is a Big Bang. Cycles of collision, expansion, slow contraction, and collision again continue indefinitely. Eternal inflation suggests our universe is just one bubble in an infinite multiverse. Inflation never completely ends globally. only locally in pocket universes like ours. The multiverse is vast beyond comprehension, containing every possible variant of physical law and initial conditions. Each of these ideas is mathematically sophisticated and motivated by deep theoretical considerations. Each makes predictions that could potentially be tested. None is proven, but none is ruled out. We stand at a moment where multiple radically different cosmologies are all viable candidates. This situation is uncomfortable for those who want definitive answers, but it's also thrilling. We're exploring truly uncharted territory. The next generation of observations, better microwave background data, gravitational wave detections, large-scale structure measurements will constrain these theories. Some will survive, others will fall away. What's remarkable is that we can even ask these questions scientifically. A century ago, the idea that we could probe the universe's origin seemed absurd. Now, we're not just probing the origin, we're probing what might have existed before the origin. This is how science extends human knowledge into seemingly impossible realms. We build instruments that see what eyes cannot. We develop mathematics that describes what intuition cannot grasp. We form theories that connect the incomprehensibly small with the incomprehensibly large. Whether the universe bounced, cycled, inflated, or began from a singularity, the answer will reshape our understanding of reality. It will tell us whether time had a beginning or extends eternally into the past. It will tell us whether our universe is all that exists or just one among infinite others. It will tell us whether the laws of physics we've discovered are fundamental or environmental. These are questions that matter not just to specialists, but to anyone who has looked up at the night sky and wondered. They connect to ancient human concerns about origins, meaning, and our place in the cosmos. Science doesn't diminish these questions. It deepens them, revealing layers of complexity and beauty that myth could only gesture toward. We don't yet know the final answer, but we know we're closer than ever before. The universe is revealing its secrets, slowly and reluctantly, but surely. Each new observation brings us a step closer to understanding where we came from. And perhaps that's the most profound realization. The universe is knowable. Reality follows laws we can discover. The greatest mysteries are not forever beyond our reach. With patience, intelligence, and the right tools, we can unravel even the deepest secrets of existence. The journey to understand what came before the Big Bang continues. New experiments are being planned. New theories are being developed. The next great discovery might happen tomorrow or in decades, but it will happen. And when it does, we'll understand our origins with a depth and precision that our ancestors couldn't imagine. This is the promise of cosmology. This is why physicists spend careers working on problems that might not be solved in their lifetimes. The question of where everything came from is worth answering, and we're finally developing the tools to answer it. If you've enjoyed this journey through pre-Big Bang cosmology, consider subscribing to Mr. Sleepy Science for more mind-bending explorations of the universe's deepest mysteries. The cosmos has many secrets left to reveal, and we're we're just getting started.